welcome to the demo of Mini IDS. Mini IDS stands for Mini Intrusion Detection System. We'll start by looking at the bus merge.v file, which we have used in this project. This is the bus merge.v file. It basically concatenates the current data word with the lower 48 bits of the previous data word, and it produces a 112-bit output. Next, we look at the comparator schematic. This is the schematic for the comparator. Here, basically, we are taking the 56-bit pattern and we are comparing it against the 56-bit data. So we have a feature called a mask, where we can mask the corresponding byte to be compared or not. Even if the pattern is recognized and the a mask bit is turned off, the comparison result will always result in as a 0. Now we look at the working of the a mask using a small demonstration. This is the data which is of 7 byte. Here all the a mask bits are 1, meaning that all of the bytes should be compared. Similarly, here the a mask bits are turned off for byte 5, byte 4, and byte 2. So these bytes will not be compared. And similarly, here in the next example, byte 2 will not be compared, and the last example, byte 5 and byte 4 will not be compared. In the next subsequent part of the demo will be completed by my teammate Partha.
Yeah, so hello guys, as my teammate told, now we'll be concentrating on the word match part. Now, as you can see here, we have 7 bytes of comparators, and we can see that there is 112 bits of data input. Here we can see that there is a wildcard input that signifies the a mask. Now the pattern that we are comparing and we need to compare is coming from the data comp input. Now each of the 7 bytes of data are compared with the total of the input in the same clock, as we can see. I'll just show you the slide here. As we can see in this slide, it's a bit clearer here. The 7 bytes are moved 1 byte to the left. Are moved 1 byte to the left and compared throughout the data to find the pattern. And moving on, we have a register 9 byte register, which is used to provide the data input that we receive. Now that all of that we have covered is put into one schematic, and the working I'll be explaining the working to you right now. Now, as you can see that there is a 9 byte input to this particular register. This particular register provides its output to the word match. The word match performs all the matching and provides a 1 bit output saying whether the particular data input is a match or not. Following that, we check the logic that we have an intent to match or not. So after the intent is successful, then we'll clock the output and give it as a matched input. Now my teammate Nikhil will carry on with the further presentation.
Yeah. Okay. So let's look at the schematic of drop FIFO. All right. So we need a way to gather all the packets that are incoming and then check the pattern. If the packets have any of the pattern that we are giving it, the input pattern, and if they match, we have to discard the packet, right? So that mechanism is taken care here. You already saw the pattern matching mechanism, how it's compared and checked, right? So how we implement it is usually using drop FIFO, right? The dropping mechanism, packet dropping and forwarding. That's implemented using drop FIFO. So first we have a dual port memory here that's generated using the IP core. So it has a write port here You can see these ports are write address, write data, write enable, and then you have reading ports here. So this is the reading, and this is the clock. Okay, so this is the read address, and it will give you the output here. All right. So what happens is every packet contains a lot of a lot of words, right? Each word is actually 72-bit wide. So in that 72 bits, the most significant 8 bits is actually control bits, and the rest of the 64 bits, that's actually the data we are going to be interested in, right? Uh, so let's look at that, where the data is coming from. All right. So you see a 9-byte register here. We're giving an input called in_54. If you look at the Verilog file that's generated, you can see where it's coming from. So so for the in54, you can see we are giving in54_control and in54_data, right? So this is the last byte of it, right? So the last byte of it that contains all the control signals, and this is the actual data we are interested in, right? So that's coming from the small 54 and fall through 54 here. So that's also given to those. Just a second. Yeah, see, in control and in data, right? So that's the actual data we are interested in. So that's coming, but we don't feed that data directly to the real port memory, right? So instead, we're gonna send it in controlled manner, right? So every time you have a packet of data, it contains a lot of words. Whenever the first word arrives, so it's gonna trigger this first word control signal here, right? That with appropriate qualification. When I say appropriate qualification, I mean the drop_packet control signal is not high, right? So if that is not there, we are letting it go through. So you can see that. So first thing, in the first clock cycle, the data is going to be there at in_54, and that is given as the data input to this. But where is the address coming from? So let's look at where the address is coming from. All right. So these part of the schematic is responsible for generation of that address. All right. So this block is basically a counter, right? If you look at the size of this, so this is actually the width of it is 72 bits, right? So that's according to a data packet, and it has 256 locations. So 256 location 54 implies that you need 8-bit address line. So that's why 8-bit counter here. So all of the clocks and the clear signals which are used for reset, synchronous reset, that are tied together here. So you can see the clear of this, all the blocks, they are tied together, and the same clock is given to all of them, right? So we were talking about the address generation for writing part, right? So initially the reset happens, but this is not enabled. So this block is not enabled, right? The counting doesn't start, but it starts when 54 write signal is high. So that 54 write signal will be high whenever the data is ready and it comes, right? So whenever the 54 write is high, the enable signal for this counter, the counter starts ticking basically. So every clock cycle it goes from 000 001 like that, right? The address keeps incrementing, and we start writing the data to the consequent location. But another thing to note is that the starting address. So there's a 54 there's a register that's here. So what that register 8-bit register is storing is actually the starting address of your first word. So you can see whenever the first word is coming in and it's not dropped, you can see this is being enabled, right? So we are storing the starting address of that. I'll tell you why that is stored, but the starting address of the byte is stored here, and also the last byte, the address of the last byte is also stored. So if we see, the data is coming from here. See, the data is coming from the address, the counter that is generating the right address. For some reason, we are storing that. I'll tell you the reason why. All right. So we were talking about the first word, right? So the first word appears and we start the counting. This enables the counting. The 54 write is enabled, so this starts counting. And also at the same time, the address of the first byte is stored here, right? So consecutively, the data is written into this, and parallelly, the pattern matching is happening. All right. So the pattern matching is happening, but let's say we hit a match for that. let's say we match the pattern. So whatever pattern we needed, that's found in one of the packets. We don't outrightly discard that packet. All right. So we'll wait for the last word to come. So we'll wait for the last word to come, and only after that we are allowing this to drop. So how are we dropping the packet? So that if we see here, for the address generation, there is something called load, right? So what happens when we when we enable this, when we set the load input high? So what happens is this, whatever the data that's coming here, that will be directly loaded to here, right? So previously, whatever the address that was generated, that's going to be wiped off, and whatever the data that's here, that's going to be loaded here. So let's see when the load will be high. So the load, if you see, is connected. See, it's connected to here, right? So as I told, whenever the pattern is found, so this drop underscore packet signal becomes high. So next clock cycle, it becomes, the load gets asserted here, right? So whenever that loading happens, so we'll go back. So let's assume we are at address 23, right? And our starting address was 1, right, in decimal, let's say. Now what happens is whenever we found that the pattern is matched, so directly whatever the starting address that was stored here, that was 1, that gets returned to the address here. So so what we are actually doing here is we are wiping off whatever that was written, and we are overwriting that data with new packet, right? So that is how we drop packets in a sense, right? So while that is the case for writing data, so let's look at what happens at the reading end. All right. So reading end, again, you have an address generator here, right? So that's actually that actually generates your read address for that's supposed to appear here. But then we are not enabling it directly, right? But we are enabling it after comparing, after obviously when it says when the 5.4 read is high, and after comparing it with something. There are two comparators here that is comparing the read address with some two other values, and only if the read address is not matching with those two values, we are letting the FIFO we are allowing the user to read, right? So let's look at what we are comparing against and why we are doing it, right? So the first comparator here, we are comparing it with this the output of this, right? So what that actually what we are doing there is that we are actually comparing it with the first word of it, right? So the first whatever that the first address of the first word was, so first comparator compares with that. All right, so we are comparing read address and the address of the first byte. For the second comparator, we are comparing the read address with the current write address of it. So only when they are not true, we are allowing the the read pointer to increment, right? So what essentially that says is that you're not allowed to read. So let's say I've written like 20 words here already in a data packet, 20 words in a data packet, right? So until and unless we check if that the pattern is not there in all 20 of that, only then we are allowing you to read packet 0, packet 1, packet 2, and then till packet 20. So that's essentially what this is doing. So my read pointer will not increment until the entire the packet, that is until it checks that all the words in that packet does not have the pattern. Only then the read pointer increments, and you're gonna get the output from out underscore 5.4. So when we actually run the behavioral simulation of this, so okay, so this is the behavioral simulation of that. And the main control signals we are the main signals we are interested in are up to out underscore control. So rest we don't need to bother about. So this is obviously the clock signal, the reset, okay, and then the input in underscore control and in underscore data is the actual input. So as I told, each data is like 72 bits wide. Out of that, the MSB 8 bits are control signals, right? So they tell you if it's the first word, first byte, the first word, last word, and stuff like that. Only 1 bit of it is used. We can use much more of it to convey other data if we require, right? So in underscore data is the 64-bit data that we are actually interested in, right? And then out underscore data is the data out that we are actually seeing. So after the drop 5.4, So this is out underscore data, right? So again, that's 72-bit wide. The MSB 8 bits are again control signals, and the out underscore data is the actual data that we are looking at. So if we look at the test bench, right? So the pattern we are giving here, right? So the pattern we are giving here is this. This is the byte. This is the bit pattern that we are giving. So whenever we find this pattern in our input data, then that data packet has to be dropped, right? So that converts to this in hex. So since this is 72-bit, this thing. So what happens is the upper bits, 8 bits of the pattern is actually the mask. So as you can see here, so this is the mask, but we haven't, since this is a 7-byte comparison that we are doing, we only consider this many bytes. The most significant bit is actually not used. So what this 111 is saying is that you have to look for the pattern and you have to match for every byte there is, right? So that's why we can ignore this, not ignore in the sense we got to know what that is, but this is the actual pattern that we are looking for. So in hex, whenever we find this pattern in any of our words in data packet, so we have to drop that entire data packet. All right, so let's see if that's happening. So yeah. So in underscore ready is saying that input is ready. All right. And then this should be here. In underscore write is that saying that, you have to start writing the data to the FIFO, right? So we see that in underscore write is still low here. And then in underscore write after at around 1000 nanosecond, it's asserted. And also in underscore control was 0, right? Altogether, it's a don't care. But right at this point, it becomes 1. So that indicates that this is the first word of the data packet, right? So this is the first word. And then that continues for quite some time. You have a lot of words in the data packet. And then after some time, at around 5000 nanoseconds, again in underscore write gets deasserted. So that's you can notice that in underscore control is 1 again here. So this is the last byte. So this is the last word of the data packet, right? So let's actually see that if that is getting reflected. So if all of these data words are actually getting reflected in the output, right? So let's start that. Let's see how. Okay. So the first word. Just a second. Yeah. So yeah, this is the first word, right? This is the first word. So 10004 ending with 10004. That's the first word. So what we see is that this is the out underscore data. So that won't be asserted. So no data will be coming through that until and unless all of the data words in that packet are examined if they have any matching pattern, right? So only the first word will be, the first word will be let to go through. So you can see that 64.10004 is coming here, right? So after that, none of the data words are being, allowed to pass through, right? So when we forward the simulation, we get to see here we have received the end word, right, of the entire data packet. So probably in two to three clock cycles, because we have a lot of flip-flops there. So probably in 2 to 3 clock cycles, we should see the data coming, because by then we would have done the pattern matching for every word there is in the packet, and we would have the result ready. So after a few clock cycles, that data starts coming in. So in this data packet, there are none of the words actually match our pattern, right? So you see, this is the pattern we were looking for. None of the words actually match that pattern. So ideally, we should not get any interruption. So we should get all the data packets. See, after this, we can see that the data packets are coming through. See, the same data packets that are coming through, right? So that happens, right? So that was there. Now again, after that, you see after the first packet, there is another set of packet of data that's coming through, right? So this indicates, so this you can discard. This is the actual first byte, or sorry, the first word of the data packet, and then it's 0 again, indicating that these are the middle range, and then this is the last word of the data packet, right? So again, here we can see that none of the data words actually match our pattern. So the target pattern is not there. So even this data packet should come through, right? So this data packet started with around 2021, right? So let's look, let's see if that is coming through. So you can see that the data packet is actually coming through, right? See, you can see that. See, this is the data packet that we were looking for, right? So after that matching, see, as soon as that data packet ends and we found that there is no pattern that is matched, 20, 21, 22, 23, 24. So that data packet goes on. So actually we are seeing that the data packet is coming through. So these were the data packets that did not have any match for the pattern, right? So now let's look at the happens to a data packet if there is some pattern in it, right? If it has a pattern that we are looking for, right? So let's look at this particular data packet. So this has a matching pattern in it, right? So let's look at what that data packet is. So it started here, right? It started at around 10,800 nanoseconds. The header is like 10035. So it starts from that, and you see there is a matching pattern. So that's the pattern we were looking for. So this packet has that word which has that pattern. So ideally that data packet should not pass through. So let's look if that happens. All right. So as I told, it starts with 35, right? So we should ideally see that 35 coming, but nothing after that. So only the first byte, the first word is led to pass through. After that, see, none of the we are not getting the data that has that the packet that has that data. See, we're not getting that. So right after that data packet is done, we'll start with another data packet that has 42 here. But this data packet is allowed to pass through. See, nothing after 30. After 30, it's not allowed to pass, but the next data packet is allowed to pass through. That means that entire data packet was dropped, right? So that verifies that our intrusion detection system along with our drop FIFO mechanism works. Thank you.